Hello everyone, I'm Linan Huang from New York University. I'm pleased to present the topic on defensive deception design for proactive cybersecurity. Attackers have evolved from being primitive to advanced persistent threats. For example, previous attacks are opportunistic. They launch a lot of attacks and then pray that someone will become the victim. Whenever there is a vulnerability, they exploit it immediately. On the contrary, APTs has specific targets such as a database to obtain confidential data or an actuator to cause physical damage. To reach the target at the final stage, APTs can go through multiple stages such as reconnaissance, initial intrusion, and lateral movements, which can last for years. The attacker's evolution has changed the game setting. Previously, the three-player security game has an attacker on one side who try to compromise the system from the external network domain, while the user and the defender cooperate on the other side to deter attacks. However, APTs can evade the boundary defense and get into our system, so the defender is forced to interact with him. Which brings two problems. The first problem is the identity falsification. Attackers can disguise as legitimate users, and the defender cannot distinguish one from the other. So the defender needs to decide the right level of trust towards the user that could be either legitimate or virtual, and take actions based on the trust level. We have developed a dynamic-based game framework to solve the problem of dynamic trust, preventive actions, and the coupling between them. The general idea of this work is as follows. Comparing with the reactive defense on the left that relies on the boundary defense and the rule-based detection, we achieve active defense based on analyzing users' behaviors to provide timely response and precautions. The defender assigns a low trust for all the users that can be either legitimate or virtual, and then obtain observations based on users' actions. And then they update their trust and then take defensive action based on the trust. The solution concept is PBNE. The Nash equilibrium characterizes the interaction among multiple players. Bayes characterize the user's uncertainty, and the perfect characterize multi-stage dynamics. PBNE involves two requirements. The first is sequential rationality, which says that if the other player follows the equilibrium for all the stages from 0 to k, any deviation from my side will not benefit my long-term utility, so that I should also follow the equilibrium. The second requirement is that the belief should be consistent, which says the trust update should always follow the Bayes rule. In the upper part, trust affects policy, and in the lower part, a policy affects trust. Therefore, there is a coupling between the forward belief update and the backward strategy computation. We use counter-prior assumption to reduce the computation complexity and develop an iterative algorithm to compute the consistent policy trust pair. The second problem is the insider threat. For intentional insiders, they are already in the system without even the need to break the boundary defense. Honeypots can help to identify malicious users. However, insiders share all the information available to legitimate users, which prevent the defender to share critical information, security information. Then the legitimate user may also access the honeypots and cause an alert fatigue problem for the defender. So the problem is how to share the right amount of security information when both types of users can know the information completely. If we share no information, legitimate users go to honeypots. And if we share full information, insiders evade honeypots. We design an overt deception mechanism to solve this dilemma. To provide an intuition, let's consider this example. Suppose each node in the network has a binary state X, which can be either a honeypot or a normal server with a prior probability B and 1 minus B respectively. The prior belief is a common knowledge, but the user, both the legitimate one and the insider, do not know the true state of the node. So the defender adopt the following deception mechanism. If the node is a honeypot, it reports itself as a honeypot with probability pi1 and as a server with probability 1 minus pi1. If the node is a server, it reports itself as a honeypot with probability pi2 and as a server with probability 1 minus pi2. Now we ask the question, what is the most effective deception concerning pi? The common sense tells us to do half-truths by letting pi1 equal to pi2 equal to 1 over half, which maximizes the entropy. However, we'll show that half-truths is in general not optimal, and the defender needs to delicately design this pi1 and the pi2 to maximize his utility by deceiving the legitimate user and the insiders to behave in the defender's favor. So the feature generator is a mapping from the site X to S. In the example, we can use pi1 and pi2 to uniquely represent pi. I have used a binary feature set for illustration, but in the honeypot example, the feature sets can be much more complicated and involve TCP/IP fingerprint, the response time, and all other features that can provide some evidence of the state of the node, whether it's a honeypot or a server. But we can show that the cardinality of the feature set can be reduced to this number without loss of generality. The A is the action site, and theta is the type site in the next slides. The user observe the features and form different posterior belief based on what feature they have observed, S1 or S2. Based on the posterior belief, the user takes action such as whether to access or not access the honeypot. The user's type can be an insider or a legitimate user. Based on the action, the state, the insider and the legitimate user will obtain different utilities. For example, if the node is a honeypot, yet the user chooses to access it, then the user receives a loss, no matter it's an insider or legitimate user. However, the loss is less for legitimate user than for an insider. I have omitted the tree branch for the red part. By using the utility difference for different type of users, we can design the generator so that the user can behave in the defender's favor. That is, the insider go to the honeypots, and the normal user only access the normal server, which helps to reduce false positive and misdetections. One unique feature of our framework is that deception is overt, as the insiders share the same information as legitimate users, so the following things are common knowledge. However, under the same observation of information, we managed to let the insider take different action from legitimate users. Therefore, we achieve an automatic and simultaneous separation of different type of users by deciding the probability of truth telling. Besides the feature generator, we further do a collective design of belief manipulator, which change the initial belief, and the incentive moderator, which change their utility to achieve a higher performance for the defender. In the literature, researchers have studied strategic information disclosure among players with private information to analyze and predict players' actions. Signaling games such as Spen's education game, Cho and Cribb's beer cash game, has a sender who sends a signal to affect the receiver's action. Dynamic-based game study another scenario for multiple decision stages where players make decisions simultaneously and can only observe the decision outcome at the next stage. Compared to the information disclosure, the focus on equilibrium analysis, strategic information design focus on an accurate design of equilibrium for better performance. So in the information design literature, there are usually one or many designers who can design the information generation and commit to it. And there are also one or many receivers who observe designer's signal and behave rationally. Previous work have studied private types for parameterization. She has studied a case where separate signals are assigned to different types of receivers to make them act differently. Glutton has investigated the possibility of making players willing to report their private information truthfully. Compared to these works, we use type to model identity falsification for insider threats and design public signal, as we cannot assign different signal to legitimate users and insiders separately. Also in the security domain, it's unlikely we can design, we can ask the insider to truthfully report their type. Contrary to information design, mechanism design methods design the location rule and the price rule for better performance. Both of them have many applications to enhance security and efficiency. Our work managed to combine both of them by collective design of the three things to incentivize insiders and disincentivize legitimate users to access honeypot at the same time. As for the results, we provided two perspectives. First, we provide a following mass program to design defensive deception. Constraints A and B requires the generator to be a valid probability measure. Since the defender and the user have different utilities, constraint C means that the defender's design of deception needs to serve the user's interest. The final constraint means that the user has the freedom not to participate. We show that the mass program is always feasible, and we also provide explicit upper and lower bound. Also, we show that the program is unbounded without the constraint of voluntary participation. The second perspective is from graphic representation and the method of Concavification. This theorem of type separability provides necessary and sufficient conditions to separate different types of users. It implies that if two types of users have completely opposite utility, then there exists no security policy that can elicit them to take the same action under any security scenarios. We further investigate the problem that when will the deception be effective? So we find the conditions where zero information and the full information will be the optimal policy. We further find that only the sign of the parameter rho 1 and rho 2 matters in determining the value of defender's optimal utility. Here is the conclusion. To meet the two challenges of adversarial deception, we designed this active and proactive defense frameworks. The active defense used adaptive learning and precautions to counter adversarial deception. The proactive defense further aimed to deceive attackers and demotivate him from launching the attack in the first place, which is more efficient than post-attack mitigation. By delicately designing the user's information and incentive, we separate legitimate users and insiders to take different actions in the defender's favor under the same information disclosure. More details can be found in our paper list below. And that's all for my work, for the talk. Thank you for your listening.